6.5, assessing normality. What that means is we're going to try and figure out if the data form a normal distribution. Assessing normality, is it normal? And so when we look through this stuff, we're looking for a couple of common themes. We want the data to be bell-shaped. So remember, that's our normal distribution, and that's basically what we want. It's not going to be perfect, but it should be roughly bell-shaped at least. Looking for outliers, and then we're doing something called a normal quantile plot. That'll be the newest piece of this information. Normal quantile plot is a graph of points x, y, where each x value is from the original set of sample data, and each y value is the corresponding z-score expected from the normal distribution. So we're going to graph a bunch of xy points, but those xy points are essentially the data numbers and a z-score. Keep in mind that z-score is going to come right from the chart. Procedure for determining if it's reasonable to assume that sample data are from a population with a normal distribution. We want to look at the histogram, and again, we're looking for that bell shape. Identify outliers. If there's more than one outlier present, we conclude it might not have a normal distribution. Notice the language of might not and reasonable. We're not necessarily going to be able to tell for sure 100%. We're kind of trying to deduce if it's possible, if it's not possible, if we think it is, if we think it's not, from a normal distribution. 3, generate a normal quantile plot. If the histogram is basically symmetric and the number of outliers is 0 or 1, do this. All right. So if these two things are in place, then we want to move on to step 3 of the normal quantile plot. Population distribution is normal if the pattern of the points is reasonably close to a straight line. So again, we've got kind of some gray language, reasonably close. All right, reasonably close. But we want these points pretty close to a straight line and does not show some pattern that is not a straight line. So if you've got dots that make some kind of pattern, that's not normal. We want the dots to form a straight line. This doesn't look like a straight line. So here are a few examples. When we're trying to figure out if something is normal or not, we look at the histogram, and if it's essentially bell-shaped, then it could be normal. And then we look at the normal quantile plot, and if this is reasonably straight, we're thinking this is normal. But as soon as you get to this other example, this does not look bell-shaped. And this one has a pattern. See how it's kind of a wave pattern? That's not a straight line. That's kind of a wave pattern. So we have not bell-shaped, not a straight line. We're thinking this is not normal. This one, not bell-shaped. We can already tell this is not going to be normal. Also, you look at these dots, all these dots, dot, 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 dot. That's not a straight line. We're thinking not normal. Tools for determining normality. Again, we want to look at the histogram and the outliers. Okay, we want roughly bell-shaped and 0 or 1 outliers. 2 or more, we're thinking it's not normal. Normal quantile plot. This is hard to do on your own because you're going to have a lot of numbers. You're going to have a lot of numbers, so I don't really want to do it by hand. We can use the TI-83, 84. We can use some other stuff. We're going to be using this website called StatDisk or one of these other things. Advanced methods. In addition to the procedures discussed in this section, there are other more advanced procedures for assessing normality, such as the chi-square goodness of fit test, the Kolmogorov-Smirnov test, the Lilliefors test, the Anderson-Darling test, the Jacques-Barra test, and the Ryan-Joyner test. We won't even get into that in this section. So more advanced. We're going to be looking at that StatDisk though, for sure. Manual construction of normal quantile plots. Manual means by hand. And so here are the steps. Step 1, sort the data from lowest to highest. Step 2 is I think step 2 is the one that's the most confusing. With a sample size of n, each value represents a proportion of 1 over n of the sample. Using the known sample size n, find these values. Seems like this comes out of nowhere, but I'll show you an example here in a second. So on and so on until you get n values. These are the cumulative areas to the left of the corresponding sample values. Cumulative areas to the left should sound familiar because that's what we've been doing in the z-table. Cumulative area to the left is exactly what we have when we look at these z-scores in the table. So they're giving us the area. We will have to find the z-scores. Step 3, use the standard normal distribution software calculator or table to find the z-score corresponding to the cumulative left areas found in step 2. We're looking for the z-scores. Probably easier to understand if you use the table, but you definitely could use your calculator. Step 4, match the original sorted data values with their corresponding z-scores found in step 3 and plot the points x, y, where each x is the original sample value and y is the z-score. So again, we're plotting these x, y points where it's going to be data value, z-score. Step 5, examine the normal quantile plot. Conclude that the population has a normal distribution if the pattern of points is reasonably close to a straight line. Reasonably close to a straight line. And the points do not show some pattern that is not a straight line. So let's do an example. Number 1, Old Faithful eruption times. Old Faithful is a geyser erupting hot steam into the air approximately 6,825 times each year. Let's consider this sample of 5 eruption durations in seconds. The question would be, and I think I left it off, but the question is, do we think these data are from a normal distribution? Right? We're trying to assess normality. We're trying to figure out if these numbers are from that normal distribution. Okay, so go back and look at the steps. Step 1 just said put them in order. So put these numbers in order. We'd have 125, 229, 234, 236, and 257. Easy enough. Step 2, I think step 2 is the hard one to understand. So understand when they say sample of 5, n equals 5. Okay, the sample of 5, we've got n equals 5, and in step 2, they told us to look at 1 over 2n, comma, 3 over 2n, comma, 5 over 2n, and so on. Now that we know that n equals 5, it's a little bit easier to understand what they want me to do. If n equaled 5, then that turns my denominators of my fractions into 2 times 5 is 10. So I'm looking at 1/10, 3/10, 5/10, and so on and so on, it said, until you get in numbers. So we can continue 7/10, 9/10. Once we get 5 numbers, that was our sample size. N equals 5, we want 5 numbers. Think of it as a decimal. It's probably going to be easier for you. 1/10, 3/10, 5/10, 7/10, 9/10. And then remember what they told you those numbers represented. Those numbers were the cumulative areas to the left. And so I think it's always useful in this chapter to go back and consider what they're talking about. They're talking about the cumulative areas to the left, and we can use that to come up with z-scores. And so that's exactly what we're going to do. Step 3, we want to find z-scores. So those purple numbers over there are areas. It would be nice to go and look at the chart. You could use your calculator. You could use the chart. But what I'm doing in this chart is I'm going to try to find that number 0.1, 0.3, 0.5. So where is 0.1? 0.1, trying to find it. Pretty close to about right here. So that number is negative 1.2012345678. That number corresponds to a z number of negative 1.28, right? Area is 0.1, z-score negative 1.28. Do the same thing for the other numbers. 0.3 is about in here somewhere, right? So we can call that negative 0.52 or so. Find the 0.5, find the 0.7, find the 0.9. We need all 5 of those numbers translated into z-scores. And so that 0.1, when you had an area of 0.1, that was negative 1.28. And an area of 0.3 was negative 0.52. Turns out that 0.5 area gives me 0 z-score, and that should make sense if you think about 0 is the middle and 0.5 is talking about 50% to the left. So that should make sense. These things are symmetrical, or this normal curve is symmetrical. So 0.7 is going to be 0.52 and 0.9 is going to be 1.28. We use the table to find those z-scores. Step 4, just find the pairs. Okay, pair up those numbers. So your first data point was 125. That was your first number. And that's going to go with a z-score of negative 1.28. And the next number was 229. This is your data. And the next z-score is negative 0.52. Third number was 234, comma 0. Fourth number is 236, comma 0.52. And a fourth number, 257, comma 1.28. That's step 4, find those numbers. Step 5, is the normal quantile plot. Basically what that means is just graph those 5 dots. Graph those 5 dots. Now the scale here is kind of weird. It does something a little bit different than what you would expect. So bear with me here. The vertical scale, what's weird about it is they put 0 kind of in the middle. And that's fine, whatever. It doesn't have to be hard. 0.5, 1, 1.5, negative 0.5, negative 1, and negative 1.5. It's a little bit strange to do it like that because we're so accustomed to having 0 down there in the corner. Whatever, it doesn't really matter. As for my X scale, I'm going to start at 120, 130, 140. 150, 160, 170, 180, 190, 200, 210, 220, 230, 240, 250, 260, and that's going to be good enough. Okay, so let's graph those points. First point, 125 comma negative 1.28. 125 comma negative 1.28 is about right there. Eyeball it up, do a nice job as good as you can. Next, you got 229 comma negative 0.52. So 229 negative 0.52 is going to be, I don't know, about right there maybe. And that's looking at like a line, but of course it does. Anytime you have 2 points, it makes a line. Let's see what happens with the other 3 points. Third point, 234 comma 0. 234 comma 0. It's about right there. 236 comma 0.52. 257 comma 1.28. Right there. It sure doesn't look like a line to me. All right, you've got those 5 dots. That doesn't lie reasonably close to a line. Doesn't seem to be reasonably close to a line. So now we can draw our conclusion. This normal quantile plot is not reasonably close to a straight line. We conclude this probably isn't from a normally distributed population. Now remember, the population has 6,825 numbers in it. This would be a ridiculous problem to have to graph 6,825 points. So thankfully I can do a sample of 5, but this sample of 5 doesn't appear to come from a population with a normal distribution. Now we're going to do something similar, but we're going to use technology. All right. So we want to go to this website, statdisk.com. Statdisk.com. So if you're on Goldadder, scroll all the way down to the bottom. Or if you want to set your favorites, I've got mine set as one of my favorites. Maybe if it'll work. Uh-oh, internet might be down. Anyway, find the one that says stat disk. That's where you want to go. Now, yours might look a little bit different than mine. I've been to the site, and so it remembers where I left off. So you're going to have to listen very carefully and follow along. If yours has a picture of textbooks and stuff, just X that out. Okay. Just X out those textbooks. You should be looking at something that looks kind of like a spreadsheet. Might look something like this. I don't know. Might have numbers in it. Hopefully not. But we want to put the numbers in it. And here's what we're going to do. Okay. So it says select the drop down for data sets. So way up at the top in the blue bar, data sets, we want elementary statistics 13 edition, and then select 23 Old Faithful. So up here at the top where it says data sets, we are the 13th edition, and then scroll down until you find 23 Old Faithful down here. And that pulls in a whole bunch of numbers. I bet there's like 6,825 numbers in there. Okay. I'm not going to go down and look at it. And it's got some different column headers. We're going to look at the one that says duration in seconds. And so once you've got these numbers in here, you're going to select the drop down for data, select histogram, and then duration seconds. So we want up here in the blue bar, data, histogram, and then in this drop down menu right here, we want duration in seconds. So that's going to pick the right column of numbers. Okay, it didn't do anything because we have to hit the green button. The green button says plot, green button says plot right there. Okay, and that gives us a histogram. That's pretty cool. All right, so remember what I said several times when we were talking about the histogram. The histogram has to basically be bell-shaped. Okay, basically a bell curve. And if you look at the part over on the right, this part is essentially bell-shaped, but the problem is we've got some outliers here. Okay, this does not appear to be from a normal distribution because we've got too many outliers. Remember earlier I said you can have one outlier, but I don't want two or more. I don't want a bunch of outliers. And in this case, you've got 5 plus 11 plus 4 equals 20 outliers. That's too many outliers. This is not going to be normal, and I can tell that from the histogram. So I want you to draw this. So we're going to draw a quick sketch of this. Draw a quick sketch of the histogram and point out any outliers. I would label the numbers here just so you can get an idea. Try to make it to scale as best you can. 46 should be lower than the 54. 2 should be lower than the 5. It's kind of hard with numbers that small. But that's a decent idea of what this thing looks like. Might not hurt to put the numbers down at the bottom. What did we have? We had 100, 150, 200. There was 100, 150, 200, 250, and 300. I believe 250 was right here, and 300 was over here. It's pretty good. I don't think I really need the numbers over on the side because I've got the numbers on top of the bars. 5, 11, 4, 5, 54, 100. Okay, so again, tell whether the histogram is bell-shaped and what that applies. Well, it's kind of bell-shaped over here,